Hello, good evening. Am I audible?
Yes, sir.
Okay. Okay. So today we will proceed with week 7 of this live session. So this is part of the Introduction to Fluid Mechanics course. So today we will be covering topics related to stream functions and like strain rate, vorticity, etc. Okay. So, So let's look at a question, then we will try to means cover the topics related to that particular this question and the related topics as well. So let's see the first question here. So here we are given a a velocity field. So this velocity field here is mentioned. A is a constant. And what is asked is what will be the physical nature of deformation of a small rectangular fluid element located within this flow field. Okay, so the velocity throughout the domain is given by this given field, and we are asked to find out what will happen to a fluid element, which is like a rectangular shaped fluid element moving around in this flow field. What will happen? So, like it is assumed to be very small rectangle. So basically, we want to find out the flow characteristics uh, uh, related for a flow related to this velocity. Okay, so first thing, let's try to do one thing. Let's try to visualize, like before getting into any mathematics related to deformation or rotation or any such thing. Let us first try to visualize what this flow will actually look like. Uh, the velocity field that has been given to us, this is a minus ay I cap plus a x j cap. Hmm. So what I will do is I will draw a coordinate axis. Let me draw coordinate axis, and then we will plot the velocities at some points to get a particular feel about what this velocity field will look like. So, so let's start with the origin. So if it is 0 comma 0, what is the velocity? If you put origin here,
Zero, sir.
yes, then it is 0. Okay, let's move to a little bit right here towards this point. And let's say this is 1 comma 0. So what is the velocity field here? If I put x is equal to 1 and y is equal to 0.
Long X A J cap.
Hmm. So if y is 0, then this is like 0 I cap plus a j cap. So A is given I think A is already mentioned that this is a positive constant. So we know the direction of this velocity. We may not know the magnitude because we don't know the value of A, but we definitely know that this is pointing in this direction, right? Okay, what about this point? This is, let's say, 0 comma 1. So here y is 1. So this will be minus ai cap, right? Because this portion is 0 and this is, if I put 1, this is minus ai cap. So if I plot that, this will be in this direction. Similarly, if I take to this point, this is minus 1 comma 0. If I put that here, I will get minus a j cap. Correct? Because y is 0 here, x is 1, so minus a j cap. So this is in the negative direction, so face it will face this way. Okay. So if I complete and like already you can see a pattern emerging here. If I complete and put this point as 0 comma minus 1, you will see this is plus AI cap plus AI cap is in this direction. So you can already see a pattern emerging here. It is like kind of like a rotating kind of a flow field, right? Mm. And even if I put some like in between points, let's say like not at the axis point, so some point like this. Let's say this is 1 comma 1. If I put 1 comma 1 here, then also I will have some minus I cap plus AJ cap. Hmm. So it is minus I cap means this, and J cap plus J cap means this. So it is like diagonally this direction, right? So if from our imagination, like we can understand what this flow, like if we see this fluid, then what this flow field will look like, right? Now, like let us try to again come back. Let us come back to the question and understand what they are trying to ask us. So they're asking, if you look at the options, they're asking whether this is a translation motion or a rotation motion. Hmm. And also they are asking about the deformations. So shear deformation and linear deformation. So uh, we have already like from our understanding of the velocity field itself, we have an idea that it is a rotational field, right? But we don't have the idea about the deformations. So for the deformations, what we generally do, um, we try to look for the okay. So what we have done so far is we are doing this first question, and here a velocity field is given to us, and we want to know what this velocity field's effect will be on a small rectangle that is inside this fluid. So what we have already seen here by plotting this simply point by point plotting this velocity field, that this is kind of having a shape like this, and like from our intuition we can understand that this velocity field will give us a rotational motion. So we have simply taken each point and plotted the direction of the velocity. So from there we understand that um, this will be a rotational motion, hmm, more or less. But we will try to have a better look by understanding how we can conclude that mathematically, and also let us try to understand what we will do about deformations. So two types of deformations is being asked here. One is the linear, and another is shear deformation. So let's come to the linear deformation. So linear deformation, let's say if I have like all these deformations, these are kinematic things. When I say kinematic, what I mean is I don't know need to know about what forces are acting on them or anything. I just need to understand like the velocity field, and that how that velocity field, the given velocity field is affecting my uh, flow, the geometry of the flow. Hmm. So that's what I am interested in here. So everything, uh, like all these deformations, are expected to be function of this velocity, because velocity is given, and like from that given velocity, we are looking at the like the flow geometry. So this will be a function of velocity for sure, and since it's a deformation, it will be some way a particular element is changing. Hmm. All these deformations, we are sure to have some sort of derivative which we will need to look at. Hmm. So del Vx, del y of v. So these deformations we will need to look at. So when we are talking about like linear deformation, what we mm, what we mean here is, if we have two points here in the fluid element, if we have 2 points here, and this is the line joining this, so there is a particular length of this fluid element. Now we want to know whether this is stretching or this is getting compressed. That's the linear deformation we are talking about. So we want to know whether this is getting stretched or if this is getting compressed. Hmm. So let's say this is in the x direction. this is oriented in the x direction. So uh, along this length of the this particular line element, uh, I will have the velocity u, component u. So I'm representing this v as u I cap plus v j cap. This is the standard notation, you already know this. So this is going with the velocity v u. Let's say this is a point B. So this is point B, and this is point A. So this is also going with a uh, x direction velocity of u. Hmm. Now, after a certain time, let's say delta t, what will happen? This will like move forward. We will move forward by a distance u into delta t, ub into delta t, and a will move forward by ua into delta t. Hmm. So something that will like help us understand this, if it is stretching or compressing, is how much they have moved, and with that motion has this distance between them changed. So we can easily get there by just subtracting this uh, like the velocities, because delta t will get common, and to find out this will be the change in length. So if I multiply delta t, this will be like a kind of change in length. So if I want to find out the strain of this particular element, what I will do, I will divide it by the length AB. I will divide it by the length AB. Now let's say AB is very small, so this will turn out to be delta U by del U del X. If this is X direction as I had mentioned, so this will turn out to be del U del X. So the strain will have delta T. Whenever we are talking about strain rate, this delta T might be dropped. So this will be strain. And whenever we are talking about strain rate, what will happen? This is simply del U del X. So this is my strain rate, and this is what we are interested here right now. When we are talking about linear deformations in a fluid, we are interested in the strain rates. uh, so this is the linear strain rate here. So this can be like given a notation like exx. Hmm, this is del u del x. So what does this give us? This gives us linear deformation. Linear deformation along the x direction, right? So along the x direction, what is the linear deformation? Similarly, we will have epsilon yy, which will give us linear deformation about the y direction. Here the velocity component will be v, and this will be like the coordinate will be y. So del v del y and del u del x. This will give us our linear deformations. Okay. So can you calculate this for this particular velocity field?
0, sir.
It is coming out to be zero, right? So del u del x is only a function of y, so del u del x is zero, and del v del y, that is also zero, because v is a function of x, not y. So this is all right. So linear deformation, there is no linear deformation, that we are now sure about. Uh, we have already covered these two derivatives, like del u del x and del v del y. But you will also have two other derivatives, right? Del u del y and del v del x. We have already understood the meanings of del u del x and del v del y, the diagonal element of this particular matrix. So, what is this matrix basically? This matrix is nothing but, if this is the velocity field, if I write using index notation, this will give me a second order tensor. When I break this second order tensor down in components, this may be written as this. Right. So these are the derivatives of the velocity basically in a two-dimensional velocity field. So we have already seen what this diagonal elements mean. Let us try to understand what is the meaning behind the off diagonal elements. Okay, so let us take this particular element. Okay, so here also their derivative is due to del x. So since this is a del x, we will again bring out back our linear element of AB, hmm, which is facing along x. So why we are taking this x-oriented element? Because we are here like talking about the x means derivative, which is uh, x like along the x direction. Hmm. So this a point A will have a velocity in the y direction, let's say VA, and this will have a velocity in the uh, y direction as well, VB. And what is this del x? This is del V del x. So del V del x, this is approximately, if this AB is very small, then this is like this can be imagined as VB minus VA by length of this AB, right? So this is basically giving us a measure of how much this there is a difference in the velocities of these 2 points. Hmm. Now, whenever you try to imagine this, you will understand that this is what is this basically trying to say is how much is this rotating in this direction, right? If B has a slightly greater velocity than A, then this element will actually give us a rotational motion. Correct? You understand this?
Yes, sir.
Hmm. Okay. For a similar element in the, let's say, which is oriented in the y direction, let's say an element like this. Here also we will have some u directional velocities, let's say UA and UB. Hmm. So this is now oriented in the y direction. Hmm. So if I try to compute this, then this is now minus UA divided by length AB, which is this length right now. Okay, this horizontal line. So this is also, what is this trying to convey? This is trying to convey when how this line is trying to rotate like this. Correct? Do you understand this?
Yes, sir.
Yeah. So now let us, we have understood the physical meaning of each and every one of these derivatives. We have understood for the diagonal ones, and now we have also understood about the rotational ones. So rotational ones, what they are trying to say, they are trying to convey like off diagonal velocity derivatives. They are trying to convey a um, uh, rotational interpretation of the velocity gradients. Okay. Now let us come back to our rectangle, because our question was for a rectangle, right? What will happen to a very small rectangle in our velocity field, in our given velocity field? So, and we are asked to find whether this will have any shear component or not. Now, what we understand by shear? What do we understand by shear? We understand that if this angle changes, then there is a shear stress. Correct? If this
Yes,
angle
yes.
changes, then there is a shear stress. When will this angle change? When if we have this two elements here, so if this tries to come this side and this tries to come this side, then this angle will change. Correct.
Yes, sir.
Hmm. So if I take the like if I try to represent this our idea, this idea in terms of our velocity gradients, then what? How would I represent this? This this first rotation, this rotation is my del v del x, right? And this second rotation is my del u del y. Okay. Now, if I add these two effects, what I will get is our my uh, shear strain rate, right? My shear rate. Correct. Do you understand
Yes,
the?
sir. Yes, sir.
Yeah. Mhm. Okay. Uh, Please calculate this and tell me. So I will write the velocity field here as well. So this is minus a y I cap plus a x j cap.
So it is still coming zero. A
It is still
minus x.
coming zero, right?
Yes,
Yes,
yes.
because del v del x, though v is a function of x, this is a, and u is a function of y. So, but this is minus a. The addition of these effects are zero. Hmm. So, there is no shear deformation. Shear deformation is also not there. Hmm. So, this I will represent by yes, epsilon x. Okay. Uh, Epsilon y because this is related to my strains, the linear deformation, and this is the shear deformation. Okay. Now, another thing that we can do with these velocity gradients is actually find out whether this is truly rotational or not. Whether this is truly rotational or not. What do I mean by this? Like, let's say we again have this rectangle, and we try to analyze what will like if it is rotational. What does that mean? That means this is having this rotation, and if I sum this up with this effect, we I talked about the opposite effect last time. So if I sum it up with this effect, hmm, like opposite of that, the del u del y, so this will give me a rotational effect. This will give me a measure of the rotation. Okay, so this will be this is del v del x, hmm, and minus del u del y. Okay, you understand, right? Why this will give me a measure of rotation? I just
Yes, sir. Yes,
like
sir.
inverted the symbol of this del u del y so that it like rotates in the same direction. Now, whether when this particular thing is giving me a like positive component, then the rotation is actually taking place. Okay, so this is represented by a vorticity. So this measure is given by a vorticity. So this is the rotation like in the xy plane. So this will be vorticity in the z axis direction. Hmm. So if you use the thumb rule, you will see that this is pointing towards positive x direction. So can you calculate this and tell me whether this is how much is this?
It will be, sir, two times of A.
Two times a, right? So this is not zero,
Yes, sir.
correct? So this is not zero. So this is 2 times A, which is not 0. So as we had already seen with our like visualization earlier, hmm, so this is kind of having a rotational motion, which is confirmed now, hmm, using. this. So this is solid body rotation. So the whole element, this whole rectangular element, this is not deforming. So none of these lengths are changing. So these lengths are not changing. Why these lengths are not changing? How do you know that? Because linear deformation is zero in both the directions. In x and y direction, linear deformation is zero. So this length is not changing. This angle, what is happening to this angle? This is also not changing. Why? The shear component is zero. So we have found out that the shear is zero. So this angle is not changing. What is only thing that is happening is that this whole rectangle is undergoing a rotation. Hmm. So if I come back to my question, uh, it is asking whether it is pure translation without linear or shear deformation. So it's not pure translation. It is pure. It is rotation. So I have my option B and option C. So it is option B is with linear deformation but zero shear deformation. This is wrong because it does not have linear deformation as well. So option C, which is without linear and shear deformation, this is correct. So option C is my correct answer here. Okay. Hmm. So here also they have explained the same thing. Hmm. So this is the linear deformations they have calculated, and they have got is as zero. Okay. So since this is a strain rate, so these are not strains, so you can put this dot here. This signifies like rate or time derivative basically. Hmm. So you can put dots instead of writing epsilon xs. Epsilon xs, this we can keep it reserved for our strains. And strain rate we can put this dot. And another thing that this is rotation. So this omega here is not actually this omega. So what I meant here is vorticity. So mm, what they have given here, this is angular velocity. Okay. So they are related. The exact relation is basically half. So if you half vorticity, you will get the angular velocity. Okay, but they have somehow calculated a two-way. I don't know. This is wrong, right? This should be A. Am I correct? Yeah, this should be A. Because A plus A, yeah. So this should be A. Okay, let's go to the. Okay, you can read this explanation also later. So this is explaining the basically the rotation thing that I explained. Okay. If you do you have any question related to this rotation and shear deformation, linear deformation?
No, sir.
Okay, let's come to this question. Next question. Uh, so two flow fields are given. And very helpful diagram is also given with the smiley faces, that what is happening. So like this um this is a very means common diagram. So like the first flow field is, I think I had discussed also earlier. So this is C1 into R. So as you are moving away from the origin, your flow field direction, your flow field velocity is increasing. So you only have the V theta component. So you have only the U theta component, U theta, V theta, whatever. Yeah, U theta component. And your UR component is zero. Both of these velocities actually have their UR component as zero. And what's the difference? This is C1 by R, and here your U theta is basically, let's say, something C2 divided by R. Hmm. So here this will occur only if there is a solid body rotation, the whole fluid is rotating. Hmm. So here you can see this, like this smiley face that has been drawn here. It is also rotating along with the fluid. Hmm. Whereas in this case, this is like a free vortex flow. It is also known as free vortex flow. So what is happening is basically this occurs if there is a point vorticity. So at this point at the middle, there is a vortex, and outside this vortex you will have this kind of a 1 by r relation, and this is basically like nothing is forcing the fluid to go around. This is moving only because of there is some kind of a wall which is moving. For example, like if you take a solid wall, solid rod, solid enough immerse it in a fluid, and around this, this is basically the top of the rod that I'm seeing here. So this rod you are rotating like this. The fluid motion that you will get will be very similar to this second diagram, this flow B. Hmm. Here the fluid is not rotating, the rod is rotating, and due to the motion of the rod, due to the viscous effects from the motion of the wall, you will get this kind of a flow field. So this is not rotational. Nothing is rotating the fluid completely. There will be actually no rotational component. Only the viscous stresses will be there. So shear stresses will be there. Hmm. And uh, this, however, this is as if there is fluid inside this particular rod. If there is fluid inside this particular cylinder, the whole fluid will rotate, and this will give you this kind of a motion. This will happen. This is also called a solid body rotation, because the solid body always rotates like this. There is a center of rotation. There the velocity is zero, and as you go mm, away from it, uh, for any rigid body or solid body, the velocity away from the center of rotation will be linearly proportional to the distance between the center of rotation and that point. Okay, so let's go to the question. What is the question? Uh, so whatever I just talked about, that they have given it in the question form. So choose the most appropriate option below. Flow A describes a solid body rotation, and flow B describes a line vortex. So is this true?
So it is as A is a solid body rotation, but B is not a line vortex.
Uh, so if you have a line vortex actually at this particular point, what is a line vortex first of all? So line vortex is basically a source of vorticity, a point source of vorticity in a two dimensional sense, and like it is kind of like this rotating rod that I said. So if you have a very small point like line which is having a rotation, then uh, that and the flow field due to that particular line. So uh, this is kind of this here the center point is kind of a singularity, right? Because the flow field here is like tending to infinity. So in this, mm, the way we can actually have this is if there is a line vortex at that particular point. If there, something which is rotating very giving it a rotational push just at this point, but has no effect outside. So outside only viscous effect is there, but at this very at this particular point, and there is a high rotational effect. Like for example, a solid rod is rotating, then you will have a velocity field like this. So this is actually a line vortex. So for a line vortex, you will have this kind of a motion. Okay, you will actually see this in models for hurricanes or like a cyclone, tornado. So there is an eye of the such storms, right? So inside the eye of that storm, you will have this linear variation of velocity. Okay. Hmm. So at the center of rotation, obviously the velocity is zero until you go to the edge of that particular eye region. The velocity is increasing linearly. Outside this, nothing is actually forcing the fluid to move around. The only thing that is giving it its velocity is this inside region which is undergoing a rotation. So here the velocity drops off in an exponential fashion, or in like inverse r 1 by r fashion. So this will drop off to zero. So this kind of a behavior. So inside this is like uh, a vortex. Now, if this vortex is now shrink such that it becomes a point, then it will become actually a line vortex. Like it is not exactly a point because this is a three-dimensional flow. We are like viewing it in a two-dimensional sense. So this will actually be a line. This is currently a cylinder. This will become a line if I shrink its radius. So that is what is known as line vortex, and the outside velocity field that we will get uh, is represented like this. Okay, am I clear?
Sir, if we are not
Yes.
considering the point of singularity, then it is a line element or a free vortex.
This is a free vortex. This is a free vortex flow.
Yes, sir.
So we have to consider the line element as well. Like line element is actually what is driving this flow,
Okay,
right?
sir.
Hmm.
Yes,
So basically, if you have like this example, if you this if this cylinder is shrinked to a line, then you will get this kind of a velocity, and that is what is called a line vortex. Hmm. So if that is what is called a line vortex. If you have means extended this cylinder is extended, not a line, then this is like a forced vortex. It means inside is forced vortex, outside is free vortex. So inside this is forced. Forced why? This is as if something is like some force is like there is some outside force which is moving this fluid. Hmm. And this is free because no force is required here. This is only moving because of the viscous stresses. Hmm. Being attached to this cylinder, it is moving. So inside this is forced, outside this is free. So this is free vortex. This is definitely a free vortex. This is a line vortex. In case of a line vortex, you will get such a flow field. Okay. Do you have any other question?
no, sir.
Okay. Uh, is option A correct?
Yes, sir.
Option is A is definitely correct. And what about option B? Flow A is irrotational. Is it irrotational?
No, sir. It is rotational.
It is definitely rotational. Hmm. And B is rotational everywhere except at the origin. Is this correct? This is exactly the opposite actually. So
Yes, sir.
B is rotational, irrotational everywhere except at the origin. At the origin, it is rotational. Otherwise, it is irrotational. So option A is correct, but B is false. This is correct. So option A is correct and B is false. Hmm. And flow A is an example of a free vortex. Is it?
No, sir. A is a force
It is
vortex.
again opposite. So A is force vortex. So this is A, and free vortex is B. Okay. Hmm. Okay. Okay. Here they have calculated. You can calculate this the rotation. Hmm. The rotation part you can calculate. So earlier we did this. Hmm. Del V del Y minus del U del X. So same thing you can do here as well to find out whether this is rotation or not. Hmm. So you already know the velocity field, right? This is c1 into r, and ur is 0, and here u theta is c2 by r. Hmm. So here first you have to convert it into r theta components. So in r theta sense, this like velocity, hmm, this will become 1 by r del r into ur by del r minus, there will obviously be a minus because of the like we are trying to consider the rotation effect and not the shear one. So this will be again 1 by r del u theta del theta. Hmm. I sorry, I think I yes, obviously. So here like here also I did the mistake. Sorry, I'll just correct it. So here we are talking about the off diagonal component. So off diagonal components means if it is like y directional, then x is the like its derivative is taken of x. If x directional velocity is here, then derivative is taken with respect to y. Here also the same thing. So r derivative, this will be of theta component, and derivative x derivative will be of the uh, R component. Hmm. So make this correction. So UR is zero. So this portion will be zero, right? So what is this when velocity your u theta is c1 into r? When u theta is c1 into r, what is this? This is 1 by r. Hmm. C1 is constant, and here this is del del r of r square. So 2r. So this is 2c1, right? And when u theta is equal to c2 by r, then what this will be? So C2 by R will cancel out, and the derivative of a constant is zero. So this will be zero. Okay, is this clear? Is there any doubt?
Yes, sir, clear.
Okay, so let's move. Okay, you may like read this notation. So these are explaining your free vortex and force vortex. So force vortex, it is forced because there is like the means the whole fluid is like forced to move in a circular motion, whereas in free vortex, like there is nothing forcing the fluid particles, they are just moving because of the viscous stresses. Okay. uh, all right, so now here this is just calculation. So you can do one velocity field is given, and you have to find out angular deformation, epsilon xy, and the vorticity. Hmm. So epsilon xy, this is given by your addition of the two components, right? Hmm. So this is del u del x plus del v del y, and put in the components here. So x into y, derivative with respect to x, partial derivative with respect to x. So y will be kept constant. So you will have y. Hmm. And notice there is no like these are already done with components, so there will be no vector signs here. So like when we are taking u, we are only taking the x component, and x component is not a vector. The whole thing is a vector which has different components. So there will be no I cap or j cap here. So this is y. V derivative we will take partial derivative with respect to y. So this minus x square, this will vanish, and this will be 2y. Right? Oh, okay. Yeah, I am again. This derivatives will be actually reversed. The derivatives will be reversed. We are talking about shear here. So the derivatives will be reversed. So when x component is there, it will be y derivative. Y component is there, x derivative. Like be like careful of this. So this will be x and this will be minus 2x. So here y square will vanish. This will be minus 2x. So the answer is here minus x. Is calculate the vorticity. So here they have used capital omega. You may use small omega as well. So this will be del v del x minus del u del y. So for v x derivative, u y derivative. Del v del x is again same thing. Actually, we have already done this here. So minus 2x and this is minus x. So this is minus 3. Okay. So option B should be the correct one. So you might all like know this, but let me reiterate. The vorticity is actually a vector. So this vector is given by uh, the cross product of the gradient sign and the velocity. Hmm. So like you can calculate this like cross products are calculated. Just that instead of instead of another vector, here is a gradient operator. So here the operator will be there, del del x, del y, del z, and here the velocity components will be there. So this can be used to calculate the vorticity. And now here, since the this z component is zero, like this is a two-dimensional velocity field, so there is no z component here. So this reduces to just our uh, k component of the vorticity. So since this is zero, this will be just like the k component of the vorticity, which is basically del del v del x. So what we were doing, we were k cap. Okay. Have you done the previous question? This question is completed.
Yes, sir.
Okay. So you can attempt this question, question number 4. Here they have basically asked whether this is uh, velocity field is incompressible or compressible and rotationally rotation. So two things are asked. So here basically for incompressible you will have to find the gradient, so the divergence, and for rotation you have to find the vorticity. If vorticity is zero, there is no rotation. If divergence is uh, zero, then there is no compression. There is incompressible. So, if you do you remember the explanations for this? I think like in our first lecture or something, we had briefly discussed about why like divergence is so important and why this is connected with the this compressibility of a flow field. I hope you remember that.
Yes, sir.
Okay.
So it will be D, sir, rotational and compressible.
Rotational and incompressible. So A,
Yes, sir.
rotational and incompressible. Let's see. So let me do it once. So grad dot B, this is del U del X plus del V del Y. Right. So del U del X is 4.
Yes, sir.
Hmm.
That will be 4.
And this is minus 4.
Yes, sir.
So this is 0. Okay. What about this? So we are
Verticity,
only considering the k component, right? The z component. Right? Hmm. So tell me, how much is this?
say 1
This is minus 1.
is minus 1, and that
This
will
is
be,
minus 1, and this is also minus 1.
yes, sir, minus
So
2.
this is minus 2. Hmm. So this is incompressible, but this is definitely
It,
rotational.
it is there, yes, sir.
Hmm. So yeah, they have calculated it here. So here they have used the angular velocity. So this is angular velocity. You may use angular velocity or uh, the vorticity, both are like representing the same thing. Okay, all right. So now we are moving towards a concept called stream function. So here a two-dimensional velocity field is given, and what we have to find is we have to find stream function. So before finding stream function, we must understand what is the stream function and why that is like useful for us. And like best thing way to like understand this is this incompressible equation. Hmm. So we have this if it's an incompressible flow, we have this equation, right? Hmm. Now, we know how to break it down. We have already done this. Uh, so del u del x plus del v del y. This is equal to 0. This is my incompressible flow equation. So now stream function is defined in such a way that this equation is actually always satisfied. Hmm. So how is this uh, done? So we define a function psi such that u is del psi del y, del psi del y, and v is minus del psi del x. Now, if you substitute it here, this u instead of u you write del psi del y, you will get del square psi del x del y, and here you will get minus del square psi del y del x. So if this is interchangeable, which is like if for like nicely behaving functions, it is the case. So this will identically always be 0. So if a stream function can be defined of a velocity field, it already guarantees that the velocity field is incompressible. So if a stream function is given, we don't need to solve a particular equation. We don't need to solve the continuity equation while we are solving for the flow field. Okay. Now, why is it given us a name of stream function? Hmm. The stream function name, as you will see, like this is given because like for a particular streamline, the this will have a very same value. It will have the same value. It will have a constant value. So like every streamline will have a constant value for a stream function that we can later on see. Hmm. So for finding this question is now for to find stream function. So for finding stream function, let us first confirm whether this is actually an incompressible flow or not. Because if it is not an incompressible flow, then there is no stream function to exist. Hmm. So if I just put it here, del u del x This is del u del x is how much? 1. So del u del x is 1 and del v del y is minus 1. So this is 0. So stream function definitely can be defined in this case. So what we have to do is we have to solve this two equations to find out our stream function. So let's take the first equation. So u is x minus y. So x minus y is del psi del y. So we will simply integrate. So psi, which is a function of x and y, definitely it's a function of both an x and y. This is equal to integration of uh, x minus y dy. And whatever this integration will be, there will be an integration constant, but here that constant will definitely be a function of x. Since the integration is done on with respect to y, the constant is not a function of y, but this can definitely be a function of x. So we will write a function of x instead of writing our usual our like usual constant of integration. So if I just integrate this, so like our partial derivatives itself, we will what we will do, we will assume x to be a constant and integrate. So since x and y are independent functions, we are able to do this. If x was dependent on y in any way, we will not be able to do this. But since x and y both are independent variables, we are able to do this type of an integration. So x dy will be simply xy. What is minus y dy? Y dy is minus y square by 2, right? Is simple integration plus a function of x. It might be any function. Let's like to determine this function of x only, we have to also solve this second equation and then compare. So v is minus y. We'll put minus y here, and minus y is equal to minus del psi del x. So let's solve this. Again, we will write this psi x comma y. Psi is a function of x and y here. So this is simply y dx. So integration y dx here, this is plus a function of y. So here similarly integration is done with respect to x. So the constant of if integration will definitely not have x, but there is no reason that it cannot have y. So it may have y. Hmm. So this is x into y plus a function of y. Okay. Now what we will do, okay, let's do it. Let's continue here. So I will write down the two expressions that we have got. So from the first equation, what we got is xy minus y square by 2 into plus function of x. From the second equation, what we got? We got xy plus a function of y. Now what we have to do, we have to compare these two equations and try to find out the general expression for psi. So like comparing, you can like fairly quickly understand that g of y, this is equal to minus y square by 2 plus f of x. Correct? It is clear till now.
Yes, sir.
Hmm. Now what we will do, what is f of x and g of y, how we will understand? So clearly, this is a g of y is a function of y, which is equal to minus y square by 2 plus there is a function of x here. But clearly, x it should not be a function of x, right? G of y should not be a function of x. There should not be an x in the right hand side. Since in my left hand side there is a function of y, there should not be a x dependence in my right hand side. So best this function of x can be, this function of x can only be a constant. It cannot be a function of uh, x. Like it cannot be dependent on x because on right hand side there should be no x. It will definitely not be dependent on y because this is like itself function of x. F of x is function of x, so it will not be dependent on y. If it is not dependent on x and y, then it will be a constant. So what we got from this argument, we got g of y as this function. We can simply put it here. So what is our stream function expression, or in stream function final expression is xy minus y square by 2 plus c, where c is a constant. So this constant will definitely come because we just integrated. A constant of integration must appear. Hmm. Okay, is the solution clear?
Yes, sir.
Okay.
Yes, sir.
Hmm. Okay. Which option is this matching with? This is matching with the first option.
First option.
Hmm. This is matching with the first option. So they have done this like calculation here also, like you can like follow this calculation. So what they have done is they have already introduced the constant of integration, but you may not as well, because your function of x and function of y can obviously contain a constant of integration. So means you may not unnecessarily put constant of, like, this is redundant. You can understand, right? This is redundant. If you don't write plus c1 here also, then also this expression is definitely correct. Hmm. Okay. Uh, let's go to the next question. Hmm. So this is a very straightforward question. So a velocity field is again given. What we have to do is we have to find the linear strain rate. So can you do that? So linear strain rate in x direction, which is basically this. So we have already like done this. What is this? This is minus 1.6, right?
Yes, sir.
This is minus 1.6. A very straightforward question. Hmm. So simply we are taking this component, this here, this is our u, this we are taking and making a derivative with respect to x. 2.5 minus 1.6x, this is minus 1.6. Okay. So, okay, same velocity field. The question is different. Question is now vorticity. What is the vorticity of this field? So vorticity also we know this is del v del x minus. Just have to find out this. Tell me what this will be.
B, sir, 0.
This is zero. Yeah, both of these components are zero. Del v del x is also zero because there is no x dependence in the y velocity. There is no y dependence in the x velocity. So this is also zero. Hmm. So vorticity is zero. So this flow is irrotational, right? There is no rotational component involved in this flow. Is there any shear component in this velocity field? Did you get my question?
No, sir, no shear component.
No shear component, because again, like both the off diagonal terms of the velocity gradient tensor is zero. Okay. There is y deformation here. Y deformation is there. Linear deformation, linear strain rate for y direction. Is linear strain rate for y direction there? I'm asking whether this is present or not. This will be
Yes, sir, that will be 0 also.
Why? What is this?
It's
This is del V del Y, right?
del V del
So,
y plus
hmm. No,
del
no,
V del
this
y.
is simply linear deformation, no? Linear
Okay,
slope.
yes, yes,
So only
yes,
one
yes,
component will be there, right? The diagonal component, del V del Y.
yes, sir.
So so
1.6.
is this 1.6? This is 1.6. Hmm. So this is a non-zero. So linear deformation in both x direction and y direction are present. But there is no shear, there is no vorticity. Hmm. So can you like try to imagine what this will look like? This velocity field will look like. So I will give you like few means like examples. Hmm. So let's say like this is the coordinate axis. So let me give you three options. Hmm. So one option is like this. Hmm. So there are means these are the streamlines basically. Okay. Another option is like this. Hmm. Uh, hmm. Okay. So like within these two only like you can understand that this will not be the case, right?
Yes, sir, there is rotation.
Hmm. Definitely this is not the case. Is this the case? Is the second case possible? The second case is actually very much possible because, like, if
Yes,
you see, hmm, in this region, the velocity will be uh, in the negative x direction, right? In the negative x direction and in the positive y direction, there will be a positive y component also. So something like this. Hmm. So like may not be exactly meeting at origin, it will be offshifted from origin, obviously, because like in the origin you can find a velocity. If you put 0, comma 0, there is a velocity. So this is offshifted from origin, but the shape will be like this. Okay. If you imagine the shape will be like this. Okay.
yes, sir.
Hmm. Also, this is a incompressible flow. So this is very much possible. This kind of flow field is very much possible. If you find out del x and del y, if you add them up, this is zero. Okay. Yeah. So let's come to this question. This is probably the last question here. So again, a velocity field is given, but this question is a little bit different. Here, a pressure field is also given. So pressure field is given, and what is basically asked is find the expression for rate of change of pressure. So rate of change of pressure following a fluid particle. So this portion is very important here. Following a fluid particle. So what will you do? What is the thing that you need to find? Can you tell me what is the thing that you need to find?
Sir, maybe stream function between 2 points.
Hmm?
The stream function, if
No,
you are considering
this has no relation with the stream function. So it is asking about the pressure. There is no stream function. Hmm. Is asking about change rate of change of pressure. So like we have to find out pressure derivative. So rate of change of pressure means there will be a time derivative. Hmm. But what kind of a time derivative? That's the thing. So will it be del p del t? Will this suffice? But what is del p del t? It is time derivative, rate of change of pressure. This is definitely rate of change of pressure, but this is rate of change of pressure of a particular point fixed in space. Because when we solve fluid mechanics, we are generally using an Eulerian frame. So we are like space is fixed, the fluid is moving. So whenever we are taking just a time derivative without any special consideration of x, y, and z, then what we are doing, we are finding a rate of change of pressure at a particular point. But it's not asking about a particular point. What is asking? It is asking following a fluid particle. What is following a fluid particle? Is it Eulerian? It is not Eulerian.
Lagrange.
This is Lagrange. So what we need to find, which derivative? Derivative we need to find here? We need to find the material derivative, capital D. We need to find the capital D, this material derivative of pressure. If we want to find the rate of change of pressure following a particular fluid particle, then we will need to use material derivative. Because what does material derivative do? Material derivative shifts our perspective from an Eulerian reference frame to a Lagrangian one. Okay, is this understood why we are using this material derivative?
Yes, sir.
Hmm. So you can now the problem is very simple. What is how do we expand this? We use our like notation. That's why velocity is given. Velocity is required here. Velocity is required here. So we need to find this. Okay. Can you do this? What is the first term? First term is zero, right? Del P del T, this is zero because there is no time here. There is no
Yes, sir.
explicit dependent on time here. So this is the only thing that is contributing to this pressure change is actually that it is moving. Hmm. Otherwise, if you see at a particular point, there is no change in pressure, like with time. So the rate of change of pressure at a particular point, fixed in space, is zero here. But still, you will find rate of change of pressure if you follow a fluid particle that you will get from this convective term. Hmm.
So it will be coming somewhat minus rho by 2, 2 u naught b plus 2 x
Okay.
b square.
Can you match with these options? Any of this?
So b.
Okay. Let me also do it here. So we just have this component, right? So if I expand this, uh, my this is a two dimension, so there is no z direction here.
Yes, sir.
So I will have u0 u0 plus bx. This is into del x of p plus I will have minus dy del y of p. Now let me compute del x of p. So del x of p here, I have x term here, I have an x term here. So let me compute del x of p. This is minus rho by 2 will be there. Minus rho by 2 will be there. And other than that, 2
U
u0
naught, U naught, U
uh,
naught, 0, P,
b. Can you tell me what the other term will be?
2x B square.
2x. Okay. And can you tell me the y derivative?
Will be 2y B
This
square.
will be there. And this is 2yb square.
Yes, sir.
Okay. So, yes, that is correct. So, I will now put this here, and this row by 2 will definitely come forward. Actually, I can cancel the 2 here. I can cancel the 2 here. I am only able to cancel this because both these terms have 2. Okay. So, like, definitely I cannot cancel otherwise. Since both of these I can take 2 common, I can cancel like this. Okay. So, I am substituting it here. Hmm. So, I can take row common as is done in the options. So, I'm just following that. So, if I have this here, then this is uh, I can take b common. Hmm. So here minus sign is there, minus is there, and like if I substitute it here, you can say if I take like b common, then I will have u0 plus xb, which is same as this. Hmm. So if I take b common here, then this will be simply u0 plus xb whole square. Right? This is correct.
Yes, sir.
Hmm. And here I have again minus. So here I have minus of minus, right? There are two minuses, so this is plus. By is there, and here yb square is there. So this is b cube and y square. Hmm. But my options I can see they are like written in a different way. So I think I need to expand this whole square term, right? I will
Yes, sir.
need to expand this whole square term. So if I expand uh, b cube y is all here, so I will take the b cube here, and there will be one b cube term here. Hmm. So this will be the x square term. So y square is here, and x square b square will be there, which is multiplied by b. So if I take b common here, this is minus b square. Correct. Hmm. So, and what is remaining? Remaining is minus 2b u0, so b square, since two b's are here, x, and minus b u0 square. Yeah. So, if I compare, I think this last option is correct,
Yes, sir.
right?
D.
Last option is correct. If I take u0 common, then from the second term, then I will exactly get this. Okay. Yeah. So here also they have done this calculation. You can go through this. Do you have any question related to today's content, the topics that we have covered today? Any questions? Okay, if there are no
Sir, what
questions,
do
then
you,
yeah, yeah, definitely.
sir, in course we have discussed also about circulation. So how is the circulation will vary along the ports or kilometers?
So, circulation, like how will you define circulation? So we have studied vorticity here, right? So what is vorticity? This is the curl of velocity, right?
Yes, circular velocity.
Mm. And how is circulation defined then?
Vorticity along a
Along a
straight line or a
yes. So along a
line.
contour, along a contour,
Yes, sir, contour. Yes, sir.
if I integrate, then I will need to find some empty space. Okay, let me use this, replace this space. Hmm. So yeah, so circulation. Hmm. So circulation, this is defined like this, right? So if omega, if I this this. Hmm. So what is your question? Now, like I will come back to your question. What is your question?
Sir, there is one question in assignment that is given in case of force vortex. Is circulation have some value or it is zero?
In force vortex, like does vorticity have value?
Yes, sir.
It has value, right? And like is any contour mentioned like where this circulation is defined?
No, sir.
Hmm. So this will like definitely have a value. It will have a non-zero value. If like means if it is mentioned like throughout means we can define our own contours, then obviously since vorticity has a value, and you can define contours through which this circulation will have a non-zero value.
Yes,
Right.
yes.
If I have force vortex in a like let's say like in a circular space, I am having a force vortex. So inside the circular space, we have seen that we will get a value of our vorticity. If you calculate, I think this will come out to like if the this is C1 into R, then this vorticity might come out to be some 2C1, I guess. So and this is constant throughout this. So if you take an integration, then obviously you will get a non-zero value of circulation. Hmm. Whereas that is not true for the for free vortex. For free vortex,
Yes,
circulation will
yes,
be
sir.
zero. Hmm. Okay. So there is like another like interesting means thing about circulation. Circulation is also like used to calculate lift. So if there is non-zero for circulation, and like you have some body inside this. Hmm. So let's say like you have an aeroplane wing. So aeroplane wings are many times drawn like this. So what is this mean? This is like a cross section of the wing. So if I have circulation over this, hmm, so like if I define a contour around this and I find that the circulation value is non-zero, then I can like say that this airfoil, like due to the flow around this airfoil, a lift is being generated. There is a certain amount of force which is acting on it because of the flow pattern, because of the vorticity around it. Okay, is there any other question?
No, sir.
Is this understood?
Yes, sir. Yes.
This part is understood, right? Okay. Mhm. Okay. If there is another any other question, you can like ask me in the next session, and like you can also like this is uploaded to YouTube, so I guess you will have the YouTube link, so you can ask there as well. Mm. Okay. All right. So I'm ending this session if there is no question.
Thank you, sir.
Mhm.